Hello friends, good morning to all of you. Again, welcome back to LNT College Multimedia Studio. Today's I have brought a more interesting and exciting topics in inorganic chemistry. So that is coordination chemistry of alkaline earth metals. As in the previous lectures, we have given a clue about the complex formation tendency of alkaline earth metals. Now, we are interested to give emphasis with special donors, that is oxygen and nitrogen donors, to form a complexes with alkaline earth metals, right? So now let's start the chemistry of oxygen and nitrogen donor Lewis bases, that is called ligands, right? So as you know that alkaline earth metals like beryllium and magnesium, calcium and strontium and barium, and this is your radium. So this is the group of all alkaline earth metals. All these metals, as you know that they exist as divalent cations, and because of low ionization energy and negative standard reduction potentials, and you can say low electron affinity, so this will give rise to formation of divalent metal cation. So this is actually metal solid. Once it is dissolved, um, or energy is supplied, then this is converted into M2 plus aqueous plus 2 electron. Now this balance 2 electron is released, so gain it gains a noble gas configuration, right? Noble gas configuration. Because of vacant orbitals, so you can simply say that is 2s and 2p in lower or top metals. In case of beryllium, so and magnesium, actually 2s and 2p, so they are vacant. So overall this M2 plus for beryllium 2 plus or magnesium 2 plus actually contains 4 orbitals, right? 4 orbitals. So these 4 orbitals are responsible to form a bond. So the bonds may be either covalent or coordinates depending on the nature of that particular ligands, right? And metal ligand interactions. So here in this particular lectures, we have actually brought these 4 points, right? So these 4 points are basically magnesium 2 plus ADTA complex, and second one is Mg2 plus porphyrin complex, and beryllium 2 plus oxalate complex, and fourth one is the basic beryllium acetate. In the previous lecture, we have also given the complex formation tendency of beryllium 2 plus with respect to acetate ions. So that is called basic beryllium acetate. So we will especially focus today on nitrogen oxygen donors to form complexes, right? So oxygen donors means you know that, so that is ethers, beta diketone or acetyl acetone, that is H2O, hydroxy and catechol. So these are the oxygen donor uh, Lewis acids, this is Lewis bases, they are called ligands. And another one is nitrogen donors, that is ammonia and substituted ammonia, diethylamine or triethylamine, right? So what happens here, actually once we talk about EDTA, so this is the EDTA, that is actually full form of ethylene diamine tetraacetic acid. Okay, so this is the structure of EDTA, which contains two nitrogen atoms, right? So they are bonded between two carbon hydrocarbons. Okay, and this nitrogen further CH2COOH and CH2COOH, and similarly this nitrogen also contains CH2COOH, CH2COOH. Here 4 CH2COOH, right? This is 1, this is 2, and this is 3, and this is 4, right? 4 CH2COOH, and in spite of these 4 CH2COOH, there is 2 nitrogen, right? So because of 3 covalency for each nitrogen atoms, so both of the nitrogen atom possess a pair of electrons, that is lone pair, right? So both nitrogen act as a electron pair donors, which can form complex with particular metal cation, right? But here COOH, COOH, and COOH. So this is the carboxylic acid group actually, but in the pristine state, so this ADTA is not reactive, right? So because of unavailability of donating centers, or you can simply say there is low or there is a deficiency of donor in spite of two nitrogens. So what actually it is done, so once we add alkalis, that is OH minus, so it forms ADTA 4 minus. So this is a polyanion. It has 4 negative charge, right? And because of the ionization of 4 hydrogen, that is this hydrogen, this hydrogen, and this hydrogen, and this hydrogen. So there are 4 hydrogen which are supposed to be attached with oxygen atom in this organic group. So once we add hydroxide ion, 4 hydroxide ions means we are going to adding a strong base, right? So the strong base has a tendency to abstract all the protons, so that is involved in this particular structure. So this hydroxide ion that will abstract 4 hydrogen ion, so result into the formation of a polyanion, so that is called EDTA 4 minus. Now what is the beauty of this EDTA 4 ions? So this is now EDTA, right? 4 minus means this is your nitrogen, this is your CH2 and CH2. Now this is your nitrogen. So what happens? This is your CH2 and C double bond O, and this is CO minus. Similarly, CH2, C double bond O, and this is O minus. Okay. And similarly, this nitrogen also contains CH2, C double bond O, and O minus. And now CH2, C double bond O, and this is O minus, right? So for the look of symmetry, so we can just adjust the structure like that. So this is the final structure of this particular EDTA polyanions. So EDTA 4 minus is a negatively charged, high negatively charged ligands. So because of presence of 2 nitrogen donors, right? In spite of these 2 nitrogen donors, it has 4 oxygen as a negatively charged. So that is O minus, and this is also O minus, and this is also O minus, and this is also O minus. So here 4 oxygen atom, so that is present as a O negative charge. So these 4 oxygen negative charge actually act as a hard donors or hard Lewis bases, right? So this EDTA 4 minus contains 4 oxygen donors, right? And 2 nitrogen donors. As you know, because of presence of a pair of electron, right? So these 2 nitrogens can form coordinate bond with a particular metal cation, right? And these 4 oxygen donors, they can form covalent coordinate bond with a particular metal center. So overall, it has actually 6 donor sites. 6 donor sites. It means such type of polyanion Lewis base is called hexadentate ligand, right? So this is called hexadentate ligand. So hexa means there is 6 donor sites which can bond together with particular metal cation. So here we have adopted actually Mg2 plus. So beryllium 2 plus has a small and highly charged state, so it can't stabilize the structure of this particular polyanion Lewis base. So once we move from top to bottom, size of the cation increases, right? So and depending on the size and fit, so they can accommodate such type of polyanion Lewis base. So this Mg2 plus and calcium 2 plus forms more stable complexes with this particular ligand. So this is the actually order of formation of Mg2 plus, which has large tendency to form compared to calcium 2 plus and then strontium 2 plus and then barium 2 plus, right? So this Mg2 plus has suitable size, and they can accommodate and they can stabilize this particular anionic ligand, so form complexes. So as you know that this is the series of increase of size of in that particular M2 plus state. So overall, this particular EDTA4 minus is a hexadentate ligand. So these 6 donor sites can be actually are able to coordinate with a single metal cation. Here metal cation in the sense that is magnesium 2 plus. So magnesium 2 plus can form complexes with this particular ligand. So what is the actually structure of ligand? Now the structure of Mg2 plus EDTA4 minus Mg2 plus, right, plus EDTA4 minus, they form like Mg EDTA overall 2 minus charge. So Mg is the central metal in a divalent form, and EDTA exists as a EDTA 4 minus. Now how this the complexation forms? So the complexation looks like that. So this is your nitrogen, right, and this is your nitrogen. So here So this is your CH2 and this is your CH2, right? So and now this oxygen actually, so this is your oxygen and this is your oxygen. So because of this nitrogen contains CH2 C double bond O, and right. So similarly, this structure CH2, now this is your C and this is your C double bond O, right? So here now this nitrogen also contains similar to such type of group. So what is actually CH2 C double bond O and this is O, right? And similarly here it can forms like this CH2 C O double bond O. So we are trying to reorient and reorganize the structure of this particular ADTA4 minus so that it can form a complex with particular metal, that is Mg2 plus, and provides a better and suitable geometry. So now this nitrogen has a pair of electron, right? So if there is Mg2 plus present in the center of, right? So this ligand Mg2 plus, right? So what happens? These two nitrogens can form coordinate bond. Now there is negative charge and this is negative charge. So this oxygen negative charge can form such type of covalent bond because Mg2 plus prefer two negative charge, and two negative charge comes from two oxygens, right? So there is a strong electrostatic interactions between Mg2 plus and two oxygen containing single negative charge, right? So they form a covalent bond, and here two coordinate bond, and rest of the two negative charge, so they occupy axial position, so it forms such type of bond, right? So overall this Mg contains 4 plus 2, 6 bonds, right? 6 bonds. 6 bonds means this particular structure possesses coordination number 6. So Mg2 plus has 6 coordination number, means this particular structure actually is adjust in octahedral form. So the complex actually exhibits octahedron geometry, right? Octahedron means, so this is the simplest way of actually this is your metal in +2 state and 4 ligands. This is your L, this is your L, this is your L, and this is your L, and this is your L. So if this forms such type of bond, right? So such type of, and one bond in above, that is plane of this particular uh, and one bond is below. Right here, L6 M2 plus forms complexes with L6. L may be either neutral ligands or anionic ligands. So depends on the structure. So here 4 ligands, right? This is 4 ligands. They are in plane. So they form square planar complexes, right? But in the axial position to this particular planar structure, above one ligand and below one ligand. So these two bond, right? They are called axial bonds, and total there is 6 bonds. 4 equatorial bond. This is equatorial bonds, and these two are called axial bonds. So here total 6 bonds means it has octahedral geometry, and because of formation of a ring structure, so the number of atoms in this particular ring, how many atoms? So suppose this is 1 2 3 4 5. So in this particular structure, actually 5 membered rings are formed, right? And how many 5 membered rings are formed? You can count. So 1 2, right, and 3 4 and 5. So 5 membered rings are formed. 5 rings, that is 5 membered. 5 members. And you know that if a particular complex so that contain a ring structure, so they are highly stable. So because of the high lattice energy, and you can simply say stability of particular bond, and bond dissociation energy is very, very high, and because we have to break down the ring structure, so such type of actually complex or highly stable. Okay, so what happens, there is 5 membered rings, that is this is your one ring, this is your second ring, and this is your third ring, right? And one ring is due to this, that is 4, and one ring is due to this is 5th. So 5 membered, 5 ring structures are formed. So that is why Mg2 plus EDTA complex is highly stable. And another thing is that, so there is a strong electrostatic interactions, right? How? There is Mg2 plus, right, charge, and 2 oxygens carries single negative charge. So there is a strong electrostatic interaction. So this complex contains strong electrostatic coordinate bonds, and additionally they also possess uh, uh, more ring structures. So extensively we can say that this type of complex is highly stable complexes, and they are actually EDTA 4 minus is used to estimate the hardness of the water, and sometimes they are added to water to soften the waters, and analysis of water also. So this is the beauty of this particular complex. So and the complex formation tendency is very high for Mg2 plus and calcium 2 plus, and rest of the also rest of the metal cation also form complexes, but depends on the stability and other structural factors also, right? So this is the actually chemistry of Mg2 plus EDTA 4 minus, and depending on the actually pH of that particular solutions, so the complex formation tendency occurs. So such type of complexes are actually preferred in are formed in a basic medium when the pH exceeds greater than 7s, right? So then the complex is formed. And in acidic medium, complexes are also formed, but depending on the stability, so they can exist. Okay. Now, so this is the actually structure, and one thing is that is Mg2 plus porphyrin complex. So what is actually porphyrin complex? Now porphyrin. So porphyrins, you know that this is the porphyrin structure actually. Porphyrin is a macrocyclic ring. Okay, macrocyclic ligand Lewis base that contains only nitrogen donors, right? So in this particular porphyrin structure, and nitrogen is actually hard donors, so it can prefer to form complexes with hard metal cations, right? So how this porphyrin actually prepared? So this is actually obtained once a pyrrole ring. This is pyrrole, that is organic compound, and which is heterocyclic. Okay, so this heterocyclic pyrrole, once it react with formaldehyde, that is HCHO, in the presence of DDQ, they form porphyrin, right? So because of the condensation of the more number of pyrrole units with this particular CH minus CH, right? So this is minus CH, not minus here. This is actually CH group in this particular corners. So it forms a such type of porphyrin ring structure. So here one pyrrole unit, this is second pyrrole unit, this is third pyrrole unit, this is fourth pyrrole unit. So 4 pyrrole rings in the presence of HCHO, they form porphyrins, and this each pyrrole ring is bridged with CH group. It means 2 pyrrole rings, they are bridged with CH group, right? So here this is your CH group, this is your CH group, this is your CH group, and this is also a CH group. So 4 pyrrole units, they are condensed to form such type of square planar geometry. So because here that is NH, that is N, and this is also N, this is N. So 4 nitrogen and 2 nitrogen contains hydrogen atoms, right? So here only they can coordinate with 2 nitrogen, but they don't form stable complexes. So we need to remove these 2 hydrogen from that particular nitrogen centers. So that is acidic in nature. So once they react with metal salt in a divalent form, then minus 2 hydrogen is removed from the structure. Now 2 hydrogen attains as N minus, that is negative charge, right? So once the metal cation react with this particular ring structure, so this is the actually bond. 2 nitrogen forms a coordinate bond, right? So this is your coordinate bond, and because of 2 plus charge and 2 nitrogen as a negatively charged, so there is a strong electrostatic interaction, so it can form electrostatic coordinate bond. So in this way, this metal 2 plus attains 4 bond around itself, and hence this is actually square planar. So once porphyrin is attached with a metal bication, then it attains a square planar geometry, right? And one thing is that such type of structure are highly conjugated structure, right? So conjugated means, so the structure contains alternatively single and double bonds. So in this particular structure, how many double bonds? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this particular structure contains 11 pi bond. It means 22 pi electron. Either it is aromatic or non-aromatic, it must follow the Huckel's rule, that is 4n plus 2 pi electron, where n is the number of rings present. So, but here that is 22 pi electron, is means n is 5, and 4 5s are 20 plus 2 22. So this structures, although it has 4 pyrrole rings, but they contains overall 22 pi electron. Here you can't say n is equal to number of rings, rather it is a whole numbers. Sometimes it follows also number of rings, they can match the criterion of 4n plus 2 pi electrons. Okay, so this is overall aromatic macrocyclic conjugated ring structure, and which contains only hard nitrogen donors. So hard metal cation can be fitted in this particular cavity if the size of this particular cavity matches with the size of the particular metal dication. They can form complexes with this particular porphyrin ring structure. So once the metal cation actually fitted in this particular hole, so it forms a square planar geometry, right? Planar geometry. And it has more ring structure. Actually, this is 1, this is 2, and this is 3, and this is 4. So here 4 ring structures, 4 ring structure, and 4 ring structures, they contain 5 elements, so 5 membered, right? So 5 membered 4 ring structure actually stabilize the metal dication. So that is why such type of complexes are stable. And and because of the formation of the ring structure, they are not only stable, but also because of the formation of the electrostatic coordinate bond. So that is n minus and n minus, then it forms electrostatic interactions with Mg2 plus or M2 plus. So because of the electrostatic interaction between the metal dication and particular this negatively charged donor centers, so such type of complexes are very stable. So here DDQ stands for 2,3-dichloro 5,6-dicyano 1,4-benzoquinone. So this is act as a highly electron deficient center. So it has high capacity, this DDQ has high capacity to polymerize this pyrrole structure into porphyrin rings. So this is the overall structure. Now, because of the presence of the hydrocarbons on the exterior of this particular ring, so they are soluble in nonpolar solvents like benzene ether chloroforms. Okay, now, so this is your actually this is the most important complex, that is Mg, that is your porphyrin. Porphyrin. So Mg2 plus. This porphyrin is highly substituted, so it has more number of uh, uh, functional groups and substituents present, so they provides stability to that particular metal cations. So magnesium 2 plus, this is your magnesium 2 plus, form, forms 4 bonds, right? So this has a square planar structure, right? So this structures contains, that is 1 ring, 2 ring, 3 ring, 4 ring, and 5 ring, 5 membered rings. So that is actually your, this is substituted ring actually. So and 4 rings, that is A, B, C, D. 4 rings are actually from the pyrrole unit, and another one is the substituted ring. So that is 5 rings. And the overall complex formation provides a ring structure, that is 1, 2, 3, 4, 5, 6, 6 membered rings. 6 membered rings. 6 membered rings. How much? So that is 1, 2, 3, and 4. 4 rings. 4 rings. So in this particular structure, actually, 4 rings are formed through the after the coordination. So they have 6 member actually in the rings. So larger the number of in the particular rings, so it has more formation constant, high stability constant. So such type of actually complexes are highly stable. So there is a large number of substituent, that is CH2, CH2, and this is also methyl groups. So they all act as a donor substituents. So they will actually repel the electron density from the nitrogen centers towards magnesium 2 plus. So here all these centers actually works as a uh, activator of the electrons presents on that particular donor centers. And here, so this is the substituents. Actually, this unit also contains a pi bonds, one pi bond, right, in this particular structure. And because of the CO groups, and it has more chromophore structures and more conjugation, more conjugated structure here in this particular case, actually 10 pi bonds, right? So in this particular rings, there is 10 pi bonds. So actually, the chlorophyll has different structure: chlorophyll A, chlorophyll B, chlorophyll C, and chlorophyll D. So depending on the type of the chlorophylls, the variation of the pi bond occurs, right? So in this case, here in this particular host structure, so there is 10 pi bonds. You can count also. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 pi bonds are actually in this particular structures. So because of the high conjugations, they absorbs visible range or visible light. So the emissions of this particular compound is intensely deep green. So deep green, and that deep green is natural occurring chlorophylls so that are present in the green plant. And this is most important compounds because this Mg2 plus um, porphyrin, that is chlorophyll. So what actually initiates the reactions, that is 6 CO2 plus 6 H2O. Once they react in the presence of chlorophyll and in the presence of sunlight, the sunlight is a source of visible light, they actually produce C6H6, glucose, fructose, and they will liberate oxygen gas, and this oxygen gas is actually source of breathings and actually sustainability of the human life on this particular earth planet. So such type of actually chlorophyll or magnesium porphyrin complex is more significant and highly important for the green plants and for the photosynthesis. And this photosynthesis reaction actually provides oxygen, and this oxygen is for only for human lives, right? So this is the beauty of this particular metal complex and the photosynthesis reactions. So because of the formation of chelated structure and chelated rings, they are highly stable and it has very high dissociation constant. So this is the beauty of actually Mg2 plus porphyrin complexes, right? Now, you know that beryllium 2 plus oxalate complex and basic beryllium acetate. And what is beryllium 2 plus oxalate complex? That is actually oxalate means C double bond OH. This is your oxalic acid. So in the acid forms, actually it has two hydrogen atoms, so that provides acidity to this particular organic compound. Once they react with hydroxide ion OH minus to OH minus, the hydrogen ion is hydrogen ions are subject to subtraction, so result in the formation of such type of dianion. So this is called actually oxalate ion. Oxalate ion. So it has two negative charge, right? So what is actually the beauty of this? Actually, once the beryllium 2 plus aqueous or beryllium 2 plus salt is added in this particular oxalate ions, the formation of complexation occurs like that. So C, this is your C double bond O. Now this is double bond O negative, and this is double bond O negative. That is beryllium 2 plus, and once they form a electrostatic coordinate bond, but because of the unsaturation, so they can also attain another oxalate, that is O, and this is O minus, and this is O minus. This is your C, and this is your double bond, and this is your double bond O. So overall, so this is your overall they attains two negative charge, right? Four negative charge from the four oxygen centers, and 2 plus overall we can get two negative charge on this particular complex. So beryllium 2 plus actually uh, form anionic complex. So this is your anionic complex. So this type of complexes are actually formed through the oxygen donors. So this is your oxygen donors, four oxygen donors in this particular complex. So they form 1, 2, 3, 4, 5, membered, one ring, two rings. So because of the formation of the chelated ring structure in this particular complex, they are highly stable, and not only due to chelated ring structure, but there is a high electrostatic interactions. O minus, they will interact beryllium 2 plus, and beryllium 2 plus has high charge density, so electrostatic coordinate bond, and that is uh, coordinate covalent bond forms. So overall, this beryllium 2 plus has sp3 hybridization, right? So it forms a tetrahedral geometry, right? So it forms a tetrahedral geometry, right? So tetrahedral geometry is formed in this particular beryllium 2 plus oxalate complexes, and this is actually bivalent, and actually uh, monodentate, bidentate. Na, this oxalate ion is actually bidentate. So one single metal cation is coordinated with two donor sites in this particular single ligand. So in this way, uh, alkaline earth metal beryllium 2 plus, magnesium 2 plus, calcium 2 plus are highly susceptible towards oxygen and nitrogen donors. So they are actually hard Lewis bases, and they prefer to form complexes like that. So because of the chelate rings and actually more dissociation constant and high binding energy, such type of complexes are stables in case of alkaline earth metals, right? So another one is that is your uh, basic beryllium acetate, as in the previous structures, previous structure of the previous lecture. Actually we have drawn the structure of basic beryllium acetate. What is the actually chemical formula? So that is Be4O O2C CH3 का whole 6, right? So this is oxygen was present at the center of the tetrahedron, so that is your beryllium 2 plus. All the beryllium exist in plus 2 state, right? So beryllium plus 2 oxidation state, and in a abbreviated, this is your AC, and this is your AC, and this is also AC, and this is also AC, right? So one AC is due to this, and one AC is due to this. So 6 acetate ligand, that is actually CH3 C double bond O minus. 6 oxygen donors as O minus. So they are also complex of oxygen donor Lewis bases, right? So this oxygen is actually sp3, and all the berylliums are sp3 hybridized in plus 2 state. So once they are heated, they form beryllium oxide, and once they react with H2O, it forms beryllium hydroxide, right? So Be was 2. This beryllium hydroxide is actually alkaline. So this is the beauty of. They can also react with that is H2SO4 to form a barium sulfate. So once they react with H2SO4, so actually once this beryllium oxide react with H2SO4, then it forms BeSO4, that is beryllium sulfate. And if this react with HCl, so then it form beryllium chloride. So this is the actually because of formation of the beryllium oxide. So this is highly crystalline powders. As in the previous lectures, we have given the idea of and property of this particular complex, right? So such type of complexes, they are also derived from the oxygen donors, and because of the affinity towards hard beryllium 2 plus. So this is what we have actually presented here on the basis of the knowledge. So these are the complexes are actually formed through oxygen and nitrogen donor Lewis bases, right? So this is all about this particular topics. So thank you, students. I hope all of you have understand the chemistry of alkaline earth metals and its coordination chemistry. So in this particular fashion, and hopefully I understand that. So this lecture would be more beneficial and exciting and inspiring for improving your knowledge of the chemistry in the field of coordination chemistry, especially in the particular oxidation state of the metals. So these are the aspects of alkaline earth metals and their coordination chemistry. So thank you. Let's we here close the lectures. Again, I will meet you with another video. Thank you.